Hello everyone, today I'll talk about the solution to the problem extra characters in a string. We'll talk about the basic solution in this part of the video, and there will also be another video later that will talk about a faster solution that still utilizes the same basic ideas as this one. Okay, so how do we approach this problem? We know that we want to select some parts of our original word to be equal to words from the dictionary, and we have to minimize the number of letters that are not covered by that single word from a dictionary. And it might be difficult to tell at first what decision we should make. So looking at the letter, it might be difficult to tell if it should be part of this word in the dictionary or some other word, or maybe we should skip it. It might be, for instance, that we can match a long word, but also we might match two shorter words. That'll get us a better solution. So for instance, let's say that in our whole string there is some 5-letter word here that matches, but also here a smaller word matches, and here a smaller word matches. So it will be better to take those two smaller words instead of this one larger word. So this kind of situation is pretty standard. We know that in this case it might be difficult to come up with a greedy solution. It might be difficult to tell immediately what the best decision of what to do with the given letter should be, but we can use dynamic programming. And in this case, the dynamic programming formulation is very simple. That's because when we have the word, we can go by consecutive prefixes of that word and get the smallest number of extra letters in every prefix. And if we can keep doing that, we can reach the end of the word and have the solution. And how do we decide on what to do with the next letter that we add? So let's say that we have calculated for all the prefixes here their optimal solution, so the minimum number of extra letters, and we want to decide what to do with this character. Well, of course, we can just take the solution for the previous prefix and say, okay, we also skip this one character, so now we pay +1. We have one extra character, but maybe some characters may match. So for instance, if this substring is a correct word in our dictionary, then we can use it as a word, and now we look at the prefix before it, and we pay the cost of that prefix, because we have already calculated the optimal way of covering that prefix, and this part we get for free. And so, this is a standard dynamic programming formulation, and the solution would look something like this. We'll be starting with 0, because to cover an empty prefix it costs 0, and we're going to go through all the data positions, our prefix forward letter by letter. At first we take the solution for the previous prefix, and our next letter becomes an extra letter that we pay for, so we add 1 to the previous DP value, and this is our current DP value. But now we try to match every possible word in the dictionary if it fits exactly in the position ending at the letter that we're looking at. So we take its length, it should start at position, our current not included position minus the length of the word. If we have now gone before the beginning of the string, of course the word doesn't fit, it's too long. Otherwise it's possible for it to fit, and we can do a basic comparison with the word and the slice of our strings from start to end, not inclusive. And of course, if those two strings are the same, if this comparison returns true, then we can take our DP at position end and minimize it with the DP at position start. So we have fit this word in this position, and now we know, and of course we know in our DP array what the best solution to the prefix before that word starts was, which is DP of start, and we can just utilize that. And at the end, of course, we return the DP for the whole string, so the last value in the DP array. So this is the basic n to the power of 3 n cubed solution, because we have to look at every end position once, so that already is n, and then also we have to look at all the words and try to match them. Matching a word takes about linear time, and so it's also linear with respect to the number of words. We have to do that for every word. This is alright for this problem, but I'll also later upload a second part of this video where we'll use the tree data structure to make this faster. So essentially for the tree solution, which makes this string matching for every word faster, we'll have part 2.